This is the original synchrocyclotron, built in 1957.
And CERN's first accelerator comes to life. The purpose of the synchrocyclotron is to produce and study new particles.
This thing was built to detect the decay of pions and muons, but they had sorted that out by like 1962. So for the next 30 years, it was able to be retrofitted to try out new experiments, and with that huge magnetic coil, accelerate particles to 0.8 the speed of light, all the way back in 1957. What's amazing about this entire system is how they built this before CNC or computer modeling, and look at the precision, as you can imagine, to build all of this, to maintain it, to keep it up, and to keep it relevant.
CERN demonstrates how science can unite nations and contribute to a better world.
Oh, that was amazing.
This video is brought to you by Delete Me. CERN was founded in 1954 by 12 European countries with a vision to unite scientists and share the growing cost of nuclear physics research. Initially focused on studying atomic nuclei, CERN's research quickly expanded to higher energy physics, exploring the interactions between subatomic particles. Today, CERN is a global hub for scientific collaboration with 24 member states and countless international partnerships. Over the decades, CERN has been at the forefront of groundbreaking discoveries, pushing boundaries of our understanding of the universe. CERN's layout can be a bit mind-boggling to grasp at first because it's a bit like an iceberg, where most of it is hidden underground. The majority of CERN's facilities, especially the accelerators and detectors, are located in a network of tunnels deep beneath the surface. This is essential for shielding experiments from cosmic rays and other environmental interference. While most of the action happens underground, CERN's presence pops up at 8 main sites or points around the 27-kilometer circumference of the Large Hadron Collider. These sites house surface buildings, experimental halls, and access points to the underground facilities.
So this is also the place where all the material that has to be installed is coming down. So there is an overhead crane on the top, which is lowering everything into this zone, and then it will be transported over there.
We're at 70 meters now.
Roughly 70 meters.
Roughly 71, I think I saw. The LHC is at 100 meters, right?
The depth of the LHC tunnel is not the same measured to the surface. So this has to do with the fact that, first of all, the tunnel is not really horizontal, but is slightly inclined with 4 or 5 degrees. And then, of course, also the surface is not even. So depending on where you are, at which point of the LHC tunnel, the depth is between 50, 60 meters all the way up to almost 150. The closer you get to the Jura, the deeper, of course, you have to go.
The main thing that they do here at CERN is study the little particles that make up our world, the forces that keep them together, and the origins of our universe. You know, basic stuff. Remember when they taught us in school that atoms are made of electrons, protons, and neutrons? Well, it turns out you can break those apart if you smash them together with enough force. And that is what they do here at CERN. They accelerate particles and make them crash into one another and break them apart and study the bits and pieces that remain. The collection of all these bits and pieces or elementary particles and how they interact is what particle physicists call the Standard Model. There are 17 elementary particles in the model, classified into different categories like fermions and bosons. Those are further divided into other types like quarks, leptons, and others. When you bind fermions together, you get hadrons like protons and neutrons, for example. When you combine hadrons, you get atomic nuclei like helium nuclei or lead nuclei. And when you combine atomic nuclei with electrons, you get the atoms or ions we're more familiar with. From there, it's what we learned in grade school. And that should be a pretty fundamental understanding of what we need to know for the rest of the video. A lot of the topics we cover are counterintuitive or not immediately obvious. You know what's really not obvious? How exposed your personal information is online. It's why I've been a member of our sponsor, Delete Me, for 2 years now. Delete Me is a hands-free subscription service that'll remove all your personal information that's being sold online. And it's not just a one-time scan. Just look at all these listings that have been reviewed each quarter and how the amount of exposed data is going down over time. I just got my 8th quarterly report, and Delete Me has scanned over 2,300 listings, and it's just amazing to see how the amount of data being exposed just keeps going down over time. And remember, Delete Me isn't just for you. There's family plans so you can protect your entire family and keep all of their data safe, because we all have a lot on our minds, and your privacy probably doesn't come up very often. It's why I let Delete Me stay vigilant and do all the work so I don't have to think about it. Have you ever heard the expression, if something is free, you're the product being sold? So join Delete Me and save 20% on all plans with my code Ricky. Links in the description. Huge thanks to Delete Me and you. Now back to the show. You have to accelerate the particles to break them apart, so you need a particle accelerator. There are a total of 11 operational particle accelerators currently running at CERN. And they're not just a bunch of separate accelerators. Everything here is connected.
So it all starts with a hydrogen source in a LINAC. All accelerators have their own physics, their own clients, and also are injectors for the other.
Hydrogen ions or protons are initially shot out of the linear accelerators, or LINACs, at 87% the speed of light into another circular accelerator called the booster. The booster accelerates them and injects them into the large proton synchrotron. There, they accelerate even more and are fed into the 7-kilometer long super proton synchrotron. After that, they're fed into the 27-kilometer long Large Hadron Collider, which is the largest and most powerful particle smasher in the world. Not to mention the largest and most complex machine we as humans have ever built. And I'm not just making that up. They literally have the Guinness World Record. At full speed, trillions of protons will race around the Large hadron collider's accelerator ring 11,245 times a second, traveling at 99.999991% the speed of light.
So in all the other, like the SPS is just single beam, right? Because it's just accelerating.
Only one way.
And then from here it goes into the different directions.
And when we have accelerated and we are ready, we will collapse the separation and the beam will collide in our 4 experimental areas.
At this speed, each proton has an energy of 7 TeVs. 2 beams of protons travel in opposite directions and smash head-on with an energy of 14, twice as much. The highest energy collisions on Earth. To put that into perspective, 14 TeVs per collision is so strong that by smashing just 32.5 micrograms of hydrogen atoms, you'd get the same amount of energy released by the atomic bomb dropped over Nagasaki. But that's only half the story. What happens after the collision is even more important because that's where the science happens. And that's when the detectors come in. These things are massive. Being able to see them up close is why I always dreamed about coming here. Before that, you should know that CERN is planning an even larger accelerator, 91 kilometers long, that will reach a collision energy of 100 TeVs, 7 times higher than the Large Hadron Collider. That deserves a video all by itself and a follow-up, so if you want to see that when that happens, let us know below. There's also one additional fact about CERN that will really surprise you, and that could change how we transmit information around the world, but we'll leave that for the end.
Welcome to the CCC. So this is where we control all the accelerators at CERN.
It's the central nervous system, bringing together control rooms for all the accelerators, the cryogenic distribution systems, and the technical infrastructure. The CCC was built in just 15 months as part of the Large Hadron Collider to streamline operations and improve communication between the different accelerator teams. The CCC is organized into 4 islands with a total of 39 operating tables. Each island is responsible for a certain set of machines and systems.
Here we have the proton synchrotron back here. This controls the booster and the PS. And then if you come this way, we have the IT, which is the infrastructure. This runs the cryogenics, electricity, cooling, all the things that keep this place running, and that's monitored here behind me. Then coming around this way, this is the Large Hadron Collider command center. All these screens up here, you can see there's no beam currently running, but this is where all the action would be for the LHC, obviously really big and important, has its own station. And then finally over here, this is the second biggest accelerator, the super proton synchrotron, which is this 7-kilometer loop here, and that lives behind me. Now, one really cool fact, is if you look on that wall, you'll see all the champagne bottles. Now, CERN is a science apparatus where some of the most amazing discoveries are happening. And that isn't lost on them. And they celebrate, they take opportunities to break major milestones, discoveries, and to celebrate all the wins. And that's what that wall back there is. I love that. There's so much, you can just feel the amount of energy and the people. And this is kind of a downtime. In a week or two, when this run picks back up and the LHC goes back online, this place is going to be absolutely buzzing.
Here's a fun fact. Before they built the CCC, they invented the capacitive touchscreen in 1972 to control the superproton synchrotron in the first SPS control room. And this highlights CERN's contributions to technological advancement even beyond particle physics.
One of the most interesting areas of study here at CERN is antimatter. So in the very early forming of the universe, we had matter and antimatter. And when they come into contact, they annihilate each other. That's why we're here at the antimatter factory. Now, as far as factories go, the outputs are pretty small, but some of the most cutting edge research is happening here.
They were entering an area of radiation.
Now, this is one of the places I most wanted to visit. Being a Dan Brown fan and having read Angels and Demons and knowing that this was actually happening in real life, I had to go check it out.
Okay, so what you basically see here is the world's only factory for antimatter, for antiprotons, I have to be precise. And antimatter is not some mysterious substance. It's just a sort of mirror image of normal matter. And if you think about transforming energy into stuff, E equals mc squared, you basically, every time you get a particle, you get its mirror image, its mirror particle, which has obviously the opposite charge, but also a few other symmetric properties. Now, this process can also go the other way around, where you contact matter with antimatter, and that annihilates the antimatter. And so anytime you have antimatter around us, it'll annihilate with normal matter. It'll transform into energy, which is why there's no antimatter here, except when we make it by this process of producing pairs of matter and antimatter. That's easy to do. We can get something like a few tens of millions of antiprotons in a single burst by using CERN's accelerator infrastructure. And then we use this big accelerator here to slow it down to pedestrian speeds, like 1/100th of the speed of light. And then it's investigated by 6 different experiments. And the reason why these experiments are all looking at antimatter and trying to study it very precisely is that when you go back to the Big Bang, matter and antimatter must have been formed in equal amounts. But if you look at the universe now, there's no antimatter whatsoever. So there must be a difference between the two, but this difference is not part of our standard model of physics. We don't know where this difference is coming from, where it might be hiding. And so if we're looking for a difference between matter and antimatter that could have explained how all the antimatter that was formed at the moment of the Big Bang could have disappeared, we have to find this difference somewhere without knowing where. So we're looking everywhere. Everything that we can think of measuring about antimatter, we do here. So we measure the mass, the charge, the lifetime, the magnetic moment of individual antiparticles, but also the interaction between matter and antimatter, which can be an electromagnetic interaction, it can be the weak interaction, the strong interaction, or the gravitational interaction.
We are looking at the antiproton trap. This is what they use to transport antiprotons to different facilities, for example. And this pretty much is what they had in Angels and Demons. This would have been the device, that briefcase that they were running around with. It's a little different than what I anticipated, but of course it does make sense. You've got electromagnets to keep it from hitting the walls and annihilating. It's got to be cooled down, high vacuum, all the rest. But if trapped successfully, theoretically it should last forever. But this is really important, especially because, as you can see here, the level of electromagnetic interference and buzzing and the noises is just so high that they couldn't do more fine-tuned research here. So the idea is that they could produce antiprotons, store them in this trap, and then transport them around the country or the world for further research at other facilities. But this right here is straight up Angels and Demons stuff.
We are in the Large Magnet facility at CERN, and here is where we do production of the magnet and maintenance of the magnet.
The LMF played a key role in assembling the LHC's dipole magnets, which are essential for bending the path of particles in the accelerator.
So what's the material choice for superconducting magnets?
For the actual magnet in the accelerator, we have this one. This one is niobium titanium. It's a ductile material. All the magnets in the accelerator now are done with this one. It's a really good material and it's tactile, so we can use it quite well. It doesn't need a reaction, so as soon as we have it, we can make the coil, something similar to that already with the cable, with the insulation, and then we cool it down. When you cool it down, it's already superconductive.
To give you an idea of why superconductivity is so important for particle physics, look at this. This coil can carry 16,000 amps. To do that without superconductivity, look at this. This is what you would need. This heap of copper. So where you see this currently in the magnet design, you can just imagine what that would look like if you had to replace it with this. And this also just makes everything more complicated. You can imagine how much bigger it would all get. That's pretty wild. I'm used to, like, you know, sizes for home, like 200 amp service is like 2-watt wire. I mean, this, just one of these would be unimaginable. And to deal with that, that's why superconductivity is awesome.
This is niobium titanium, and but like the one that look like a bit like copper, it's niobium 13 is the new one. The problem that we have with this cable is that we are going, like, these are pieces of niobium 13 reacted, and if you try to just do like that, they broke. So we need to build coil with this material that it's really, really brittle. But if we switch to niobium tritinium, once reacted, it's like that. So we cannot have a coil if the cable is already reacted. We need to do the coil before and then react in a coil shape.
So without that step, it wouldn't be superconductive?
No.
And as soon as it becomes superconductive, it becomes very brittle and...
And then to give mechanical stability, we have impregnation. So we put the resin to have mechanical stability, but also electrical insulation, because this one, it's really nice because we have the insulation, electrical insulation already on the cable. But if we bring this at 650 degrees, it's burning completely.
How does the stronger magnetic field then give you higher energy, right? Is it the focusing?
It's focusing. It's the shape. It's the shape of the beam. If we want the beam to collide and have higher luminosity, it's like the beam is like as the size of an air. And so if you want to collide them, you need to take two air and collide. Not super easy. Then from the collision, when we have more data, and it's easier to study the phenomenon than so when we have higher probability of collision. That is the oven, it's right there. We cannot get closer, but it's like, that's the oven for the impregnation. It's go actually to 900 degrees, but we used to up to 650 for the coil.
What's being impregnated here? I'm sorry, I just want to make sure.
In this oven here, we have the cable not superconductive that is reacted to become superconductive.
Oh, okay.
This is phase one.
And is this on the traditional cable?
No, this is on the niobium 13. This is the new one. This is the new one. All the coil we are doing is our new cable.
Okay, so you've actually solved the problems and you're actually already
manufacturing.
Yeah. No. This is a magnet with that coil, and it's the we are 80% on the series. So these magnets are working. We tested them, all of them, and they're.
So this research happens here. You're manufacturing it here.
Yes. Like the first stage was smaller magnet, not 7 meter, but 1.
Yeah.
And then now we are at 7 meter.
What you can see here, this is all real components. So these are the superconducting cables you see, they are coming. It's like if I make a circuit with several coils, I do like this, no? So in the middle, what is connecting them is the cable as well, superconducting cable. So this is the cable traveling all along, and then it's coming to a quadrupole to be connected. So these are the power converters here behind. Of course, this is nothing because they took back and they are optimizing still up to the last moment. These are big connectors, these connectors. At 20,000, when you are working with copper, you see how much copper you need. And then you remember the conductor. This is also conducting 20,000. So you see visually this huge difference. And this is a conductor that is including also the water cooling. So this is the entrance of the water.
Oh.
And this is a copper cable, because in the room temperature you have to connect somehow to your power converter. And here we have we decided this connection to do it in the rigid copper. So this is a rigid copper bar. So 20 kiloampere, you need all this copper. It's just configured in in a different way. So that was a conductor, water-cooled cable. This is a water-cooled bus bar, as we are calling.
So this is the input of 20,000 amps coming in.
Exactly.
And you can just kind of get a sense of the scale, the size. Look at these bus bars. Look at the heft of this and how many of them that you need, right? You have 4 discrete bus bars feeding through. And this is actually a really nice visual because it kind of shows you, then you can look at the size of this coming in. And finally, down to the link. So this is the superconducting link that we had talked about before. Cooled cryogenically, but it's not as cold as, it's not the 1.9 K like we need for the magnets. It's closer to 40 K, but superconducting, and it can be that small. You notice that this superconducting link is kinked. It runs along in a kind of a zigzag pattern. The reason is, from room temperature to the superconducting state, that's a 300°C drop in temperature. And when that happens, this entire link would shrink by maybe half a meter, 1.5 feet in size. So you couldn't just have a straight pipe because it would contract and actually snap off. So you have to build in that room for linear thermal expansion. So I mean, the benefits in terms of just the amount of copper, the material, the weight savings, that's why it's really interesting for things like aviation. Would you really want to have that much copper to transport megawatts of power to electric motors for your powertrain, or you want to go superconducting and make all the linkages super small and lightweight? Those benefits are going to be insane.
So this was here before the LHCb experiment. So the previous collider setup back in the 90s and 2000s, this was the detector at this location, and they deemed it more beneficial to leave it in here to use as a tour rather than try and get all of these huge pieces of lead out 100 meters up.
If you tour Atlas and CMS, their detectors look like this, but they're so large it basically fills up the whole cavern, so you don't even get to see much of it. Right. But this one, you can go right up to it. A lot of these lines are for low voltage power. A lot of them are for high voltage power. Right. And then a lot are data cables. It's a complicated 3D Tetris puzzle, where you want to maximize the amount of space that you're actually using to detect, but you also need to route your cables. These are the calorimeters. They're meant to stop particles and measure the energy
absorbed.
Yeah, essentially are big hunks of lead. Lead is the densest, heaviest material we can have without getting radioactive. Particle flies in, collides with the lead, it showers, releasing its energy, and then we can detect that energy shower.
Look at the thickness that's the radiation wall. From that yellow door, that's how thick it is, pure concrete. And now we're on the actual beam side.
Here's the individual detector components drawn on the picture. The interaction point, the collision point, happens actually back in that concrete. And that's where our velo sits. You can actually see the beam pipe if you look in between these two. The metal pipe going through the middle is the beam pipe. Back in the concrete, where you can't really see, is our vertex locator. You can see on the outside of our concrete, that's our rich detector, what we use to identify particles that come through the detector. Next step, where that guy is working right now, you have our UT, which stands for upstream tracker. The big blue thing, that's our magnet. Then after the magnet, you have our sci-fi detector, which stands for scintillating fibers. It's another tracking detector.
And then there's the absolutely awe-inspiring Atlas Cavern, home to the Atlas detector, one of the two general-purpose detectors here at the LHC. It was here, at the Atlas detector, that they discovered the Higgs boson, aka the God particle, on July 4th, 2012. This was the missing piece of the Standard Model that explained how all other particles gained their mass. Peter Higgs was awarded the Nobel Prize in Physics the following year after Atlas proved his theory right.
Okay, this might be the most powerful visual of all. So far, all the places you've seen us, those are large openings where the collectors are, where all the detectors are, where all the actual work happens. But the 27 kilometers, this is what it mostly looks like in between. And this is an area that we can never actually access. This is a mock-up to give you a sense of the scale. This is how big the tunnel is, and this is the beam right here.
Excuse me, have you seen Alice?
Yes, it's over there.
That's not Alice. What is it?
The study of the lead-ion collisions needs an enormous three-dimensional digital camera that surrounds the collision point. This is the Alice detector. It records the direction and energy of particles emerging from a collision. By analyzing millions of collisions and comparing them with theoretical models, we can learn more about the properties of this primordial state of matter.
So we're just a few weeks too late, and now they're preparing for the next run, and the doors are closed. We're not going to be able to see inside, but this is what it would look like if we had seen it. The doors open, all the detectors and everything else on the inside. That's all happening right there behind us, underneath all this concrete.
This is the new spectrometer.
Wow.
So you can see the dipole, the blue one, to band positive and negative particles. And these are the several, we call them stations, so the layers of this gaseous detector. Inside that tube, you have the beam pipe. That is a shield. Again, out there you have the concrete. This is to shield in case there is an unstable beam that you don't want to hit your detector.
So this is an actual event from the 18th of November 2022, from one collision.
You can see that here you have the collision point and all the particles coming out. You see the amount of particles produced in a lead-lead collision. And here, these towers represent the energy released in the calorimeter. So you already have a first idea of how much energy the particle has. And here you can see that there is the hadron absorber and only muon passing by in the mu spectrometer.
So there'd be muons going all over, but this is the cone of muons that we could detect here.
So here you have the beam pipe. The real beam pipe is made of beryllium, but beryllium is toxic, so this is not beryllium. So you have to imagine that the collision between either protons, or lead-lead, heavy ion in general, happens here in the center. And then you have several layers, several detectors. Why different detectors? Why different technologies? Because we don't have one single technology that tell us all the information that we want to know. You need to combine the information between the different subdetectors. So that one, it's the old inner tracking system of Alice. It was working during run 1 and run 2. You see here cut it in order to look inside. Of course, this was also covered, but again, we cut it so you can see a bit. The first thing that you can observe is that this beam pipe is bigger than the one I showed you.
Yeah.
Every time we do an upgrade, we try to go closer and closer and closer to the collision point because we want to be as precise as possible. So we need to go closer in order to better reconstruct it.
Now, there is one thing in the diagrams that I've shown you before that I didn't fully understand. Remember this diagram? It's got a little arrow that points to the southeast labeled CNGS, which stands for CERN to Gran Sasso. I didn't think much of it until now. I thought it was just a building on site called Gran Sasso. But I looked for that building and there wasn't one. Then I realized it's the only line in the entire image that ends in an arrow and not a flat black bar. And that's when I realized that it says neutrinos. Now, neutrinos are the tiniest little subatomic particles you can imagine. They're tiny and neutral, so almost nothing can stop them. I looked up Gran Sasso and it turned out to be a massive in the Apennine Mountains in Italy. And I thought that was a typo, but actually it's entirely correct. The Large Hadron Collider at CERN generates a beam of neutrinos. These things are so small, they'll go through lead walls and mountains like it was nothing. The beam is pointed in a straight line at a lab in Italy 732 kilometers away. Because of the Earth's curvature, it goes the entire trip through the rock, 11.4 kilometers below the surface at its deepest point. Now, why does this matter? Because neutrinos traveling at almost the speed of light could travel in a straight line from one point on Earth to any other, right through the core without having to go around. It's a much shorter route, and in theory, we could develop a communication system using neutrinos that transmits data much faster than any underwater fiber optic cable or any low Earth satellite system constellation like Starlink, simply because of the shorter distance. Now, of all the incredible research, science, and engineering breakthroughs happening here at CERN, this could be the one that has the most potential for commercialization. Communications is a multi-billion-dollar industry, and this could be something that we might see on the horizon. So this trip has been incredible. We've learned so much, and I want to just thank the team at CERN for this access and this privilege of a lifetime to come see everything. And if you thought this was all cool, check out this video next. Until next week, I'm Ricky Da Vinci. Thank you so much for watching.